Good morning all. Today we are going to handle the topic choice of number of poles in a DC machine. First we will see the significance of selection of number of poles in a DC machine. This equation indicates the output equation of a DC machine. You are quite familiar with this relation. In this relation C0 is actually the output coefficient that is given by the relation pi square B average AC into 10 raised to minus 3. B average is actually the specific magnetic loading and AC is actually the specific electric loading. So once if the value of C0 is known, we can easily determine the value of D square L from that. And it is from this relation we determine the main dimensions of a DC machine. While seeing the output coefficient relation, it's clear that the value of C0 is determined by the proper choice of specific magnetic loading as well as specific electric loading. From the standard relation of specific magnetic loading, we very well know that B average is equal to P phi divided by pi dl, and from the standard relation of specific electric loading we very well know that AC, that is this specific electric loading AC is equal to IZ into Z divided by pi d. From the relation of specific magnetic loading, that is B average is equal to P phi divided by pi dl, it's very clear that this specific magnetic loading is having a dependency on the number of poles. Similarly, from the standard relation of AC, that is IZ into Z divided by pi d, where IZ is actually the current flowing through each of the conductor, and this current can be determined by dividing the armature current with the total number of parallel paths. In the case of lap wound machines, this number of parallel paths is determined by the number of poles. Therefore, we can say that this particular value of specific electric loading is also having dependency over the number of poles. Therefore, we can make a conclusive statement that the number of poles used in a DC machine is having dependency both over the magnetic circuits as well as their electric circuit. In the case of AC machines, that is both in the case of induction machine as well as synchronous machines, the number of poles is determined by the speed of the machine, because in those machines there is a particular relation for synchronous speed which is actually 120 F by P. From that relation it's very clear that the speed of the machine is having dependency over the number of poles. While coming to the DC machines, any number of poles can be used. However, considering the commercial constraints, only a very small range of number of poles are generally used in the case of DC machines. Next, we are going to see the various factors which are affecting the selection of number of poles. Mainly, there are 7 factors which are affecting the choice of number of poles. We will see each one of them in detail. The first important factor is the frequency of flux reversals. The relation for frequency of flux reversal in the case of a DC machine is given by F is equal to P into small n by 2. The small n is actually the speed in RPS. If large number of poles are chosen, then definitely the frequency of flux reversal value also will be very large. This consequently will result in an excessive iron loss condition. Due to this excessive iron loss condition, the efficiency of the machine gets reduced. This is not a favorable condition. So it must be ensured that while selecting the number of poles, the value of frequency must lie between 25 to 50 Hz. The value of frequency means the frequency of flux reversal. Next factor which is affecting the selection of number of poles is weight of iron parts. The iron parts mainly comprises of the yoke area as well as the armature area. The diagram of a 2-pole machine and a 4-pole machine are given here. In this 2-pole machine, this portion is actually representing the yoke and this is the armature of the machine. If you see in this diagram, it's very clear that the flux per pole is actually phi by 2, considering the total flux of the machine is phi. Then we can say the flux per pole is phi by 2. You will be able to see that flux per pole very clearly here. So the flux over here is actually phi by 2. When it reaches the yoke portion, this flux is further getting divided into 2 and the flux which will be flowing through the yoke portion is phi by 4. Here also you will be able to see that. This is the case with the 2-pole machine. Now consider the case with 4-pole machine. If the total flux in the machine is, if the total flux means total flux in the air gap of the machine is phi, then definitely the flux per pole can be indicated as phi by 4. So when this flux per pole is reaching the yoke portion, it is getting divided into 2. So the flux which will be flowing through this yoke is phi by 8. From this 2-pole machine and 4-pole machine, it's very clear that as the number of poles are increasing, definitely the flux carried by the yoke is also getting reduced. Hence, we can say that the flux carried by this yoke is inversely proportional to the number of poles. As when the number of poles are getting increased, the flux carried by the yoke gets reduced. So, keeping the value of magnetic flux density a constant one, in order to compensate the reduced value of magnetic flux, we have to reduce the area of cross section of yoke proportionately. So it's very clear that while comparing with the case of a 2-pole machine, in the case of 4-pole machine, the area of cross section of yoke is proportionally reduced. Next, we are going to see how this weight of iron part is affecting the choice of number of poles in regard of armature core area. In the previous case, we have considered with respect to the yoke core area. Now we are going to say it with respect to armature core area. Just like how we have seen the flux per pole is getting splitted in the yoke, in the same manner the flux gets divided in the armature core also. You will be able to see that very clearly here. This total flux is actually 5/2, and here also it is getting divided into 2, so each of them will be 5/4. In this case, each of them will be 5/8. So just like how this flux is getting divided in the portion of yoke, in the same manner the flux gets divided in armature core also. Therefore, we can say that when the number of poles are getting increased, armature core cross section area required also will be less. But the basic problem which will occur while increasing the number of poles is, definitely when the number of poles are increased, the frequency of flux reversal also gets increased, which leads to excessive iron loss condition. Even though we will be able to reduce the yoke and armature core area, but increase in poles is having the negative effect of excessive iron loss, which is actually not a favorable condition. This relation is actually indicating the eddy current loss relation. Eddy current loss is directly proportional to magnetic flux density square and frequency square. So in the case of a 2-pole machine, we will be able to obtain the relation of eddy current loss after making suitable substitution like this. As I have mentioned, the flux which is flowing through the core is 5/4 in the case of 2-pole machine, whereas in the case of 4-pole machine it's actually 5/8. This 5C is indicating the flux which is flowing through the core. For P you have to make the substitution of 2 here, and here you have to make the substitution 4. Finally, we will be able to obtain the relation of eddy current loss in simplified form like this. So you will be able to see these two relations are one and the same only if the values of AC, that is armature core area, is same in both these conditions. Similarly, the relation for hysteresis loss is also given here. After making suitable substitutions, we will be able to obtain the final relations in these two forms in the case of 2-pole machines as well as 4-pole machine. From these relations, it's very clear that the value of hysteresis loss decreases with increase in number of poles. See, comparing with the 2-pole machine, in the case of 4-pole machine, definitely the value of hysteresis loss is small. In order to make this value same, you have to reduce the value of armature core area in the case of a 4-pole machine. If you are able to reduce the value of armature core area to such an extent that the value of hysteresis loss is same as that of the hysteresis loss in the case of a 2-pole machine, then we will be able to achieve the same hysteresis loss value just like how we have achieved same eddy current loss value by equating the values of armature core areas. Next factor which is affecting the selection of number of poles is armature copper. Basically, a coil consists of two parts. One is the active portion of the conductor and the other is the inactive portion of the conductor. The active portion of the conductor actually contributes to the production of torque and EMF. In the case of motor, this active portion contributes to the production of torque, whereas in the case of generator, it contributes to the production of EMF. The purpose of this inactive portion of the conductor is simply to provide the electric connection between this active portion of the conductors. This projection of inactive portion of the conductor is said to be the overhang, and the distance through which this overhang projects outwards is said to be the outhang. So if you see, in the case of a two-pole machine, comparing with the case of a four-pole machine, the length of overhang is large. By comparing this two, it's very clear that in the case of two-pole machine, comparing with that of the four-pole machine, the length of overhang is quite large. From this we can easily conclude that when the number of poles are large in number, then definitely the weight of copper required also will be quite small. This explanation is made with respect to armature copper weight. Now we will see how this field copper weight is going to influence this parameter, that is weight of copper. Just like we have seen before, when the number of poles are large, then definitely the flux per pole is quite small. And as the flux per pole is small, this further having the influence over the yoke area as well as armature core area. So it's very definite that in the case of two-pole machine, the cross-sectional area of the pole is large comparing with that of the case of a four-pole machine. In fact, double the size as that in the case of a four-pole machine. So when the number of poles are small, due to this large cross-sectional area of the poles, definitely the mean turn length of the field winding also will be large. As this mean turn length is large, hence the weight of copper and therefore the field copper loss. So it's very clear that while considering the armature copper as well as field copper, when the number of poles are small, then definitely the amount of copper required will be very large comparing with that of the large number of poles. Next factor which is influencing the selection of number of poles is the length of commutator. Consider a lap wound machine. In the case of a lap wound machine, the number of parallel paths is same as that of number of poles. First we will see a two-pole machine. In the case of two-pole lap wound machine, the number of parallel paths will be 2, whereas in the case of four-pole lap wound machine, the number of parallel paths will be 4. Therefore, the current through each parallel path will be Ia by 2. In this case, the current through each parallel path will be Ia by 4. So from this diagram, it's very clear that the current which will be coming to this brush is Ia, and which is getting splitted into two parallel paths, that is Ia by 2, Ia by 2. Similarly, if we are seeing here, the current through each parallel path is Ia by 4. So definitely the current which is coming through this brush is Ia by 2, which is getting splitted into two, Ia by 4 and Ia by 4. So it's definite that when the number of poles are increased, the current collected by each brush arm is getting reduced. See, in this case of two-pole machine, the current collected by this brush arm is Ia, whereas in the case of this four-pole machine, the current collected by this brush arm is Ia by 2. So as the number of poles are getting increased, definitely the current collected by each brush arm is also getting reduced. Due to this reduced collection of current by this brush arm while increasing the number of poles, definitely we will be able to reduce the thickness of each brush. Usually each brush covers around 2 to 3 of commutator segments. So while increasing the number of poles, due to this effect of reduction in brush thickness, effectively we will be able to reduce the commutator length. As I have mentioned now, each brush covers 2 to 3 commutator segments. So when the brush thickness is getting reduced, means definitely we will be able to reduce the length of commutator. By reducing the length of commutator, we will be able to reduce the overall length of the machine. Next parameter is labor charges. All of you are quite familiar with the standard relation, that is induced EMF is equal to 5P and Z by 60A. Instead of capital N by 60, we have written here small n. Usually you have studied in your DC machines course this relation 5P and Z by 60A, but there we have used capital A for number of parallel paths. Here we are using small a, both are on the same only. That is number of parallel paths. So from this relation we can write induced EMF is directly proportional to Zn by A. In the case of lap wound machine, This A is same as that of number of poles. Therefore, from this we can write Z is directly proportional to EP by N. Z is actually the total number of conductors in the case of DC machine. So if you are seeing in the case of wave-wound machines, the value of A always is 2. Therefore, in the case of wave-wound machine, the number of armature conductors, that is the number of armature coils, does not has any dependency on the number of poles. Whereas in the case of lap-wound machine, the number of armature conductors or the number of armature coils will be having dependency over the number of poles from this standard relation. So it's very clear that in the case of lap-wound machine, when the number of poles are getting increased, definitely the number of armature coils required will be also quite large in number. As we all know that the number of commutator segments in commutator is same as that of the number of armature coils. So definitely when number of poles is large, the number of commutator segments required also will be large in number. Moreover, the number of field coils is same as that of the number of poles. Hence, when the number of poles are large, definitely the number of field coils required also will be large in number. So it's very clear that in the case of a lap-wound machine, when the number of poles are large, definitely the number of armature coils and field coils required will be large, and hence the labor charges required for this windings also will be large. Next factor is flashover. From this diagram, it's very clear that when the number of poles are increased, then definitely for the same armature diameter and for the same commutator diameter, the distance between the adjacent brush segments has been reduced. See, in the case of this 4-pole machine, the distance between this adjacent brush segments or adjacent brushes, sorry, we won't say it as adjacent brush segments, we will say it as adjacent brush arms or adjacent brushes. So in this case of 4-pole machine, comparing with that of the 2-pole machine, the distance between this adjacent brush arms is reduced. So as the number of poles are getting increased, then definitely the distance between this adjacent brush arms also gets reduced. This reduced distance between the adjacent brush arms increase the possibility of flashover between them, which is actually not a favorable condition. Next factor determining the choice of number of poles is the armature MMF per pole. The armature MMF per poles relation is given by AC by 2 into pole pitch, where AC is actually the specific electric loading. So from this relation, it's very clear that the armature MMF per pole is inversely proportional to the number of poles. So it's definite that with smaller number of poles, the value of armature MMF per pole is very large. This further results in the distortion of the field and hence results in the reduction in flux under load conditions. That is due to the effect of armature reaction. So it must be ensured that with smaller number of poles, compensation winding must be provided in order to reduce the effects of this armature reaction. This provision of the compensation winding will further complicate the construction and increase the overall cost of the machine, which is actually not a favorable condition. The permissible limits of armature MMF for different power ratings of the machine is given here. It must be ensured that these values should not be exceeded. If these values are exceeded, means the effect of armature reaction, the inverse effect of armature reaction will be high. This is actually the conclusive points of all the factors which we have mentioned just now. We have written it in advantages and disadvantages. Next we will see the various gate lines which will decide the number of poles in a DC machine. The first gate line is the important one, which we have already discussed, that is the frequency of the flux reversal should be in the range of 25 to 50 Hz. The second important parameter is the current per parallel path should never be greater than 200 ampere. The current per parallel path is actually decided by the number of poles in the case of a lap winding machine, because when the number of poles are large, means definitely the number of parallel paths also will be large, because number of parallel paths in the case of lap winding is same as that of the number of poles. And it must be ensured that the current which is flowing through each of these parallel paths should never exceed that of the 200 ampere. The third important point is the current per brush arm should not be more than 400 ampere. And the fourth guideline is the armature MMF value should never be exceeding the values which are given in that table. So these are all the points which you must know for selecting the number of poles in the case of a DC machine. With that, we are completing today's session. This is actually a very important topic. Thank you.